welcome back, and sitting next to me is a Bendix G15. This is a full-fledged vacuum tube computer from 1956, although this one is serial number 238, so it's probably like 1958 or so. Still, this is a pre-1960s all vacuum tube computer, and it is epic, but also it's like incredibly historically significant. It was designed by Harry Huskey, who worked with Alan Turing on the Pilot Ace computer. And a lot of the design influences that went into the Ace also found their way into the Bendix G15. So this is an incredibly important machine in the history of computing, which raises the question of who on earth let me get my hands on one and how did it end up here? Well, this one is on loan from Bob over at System Source Museum, and if you haven't heard of System Source Museum, go check them out immediately. It's one of the greatest collections of computing history in the country, probably in the world, but what I love the most about the museum is that a lot of the machines are functional. The big UNIVAC that's the size of a New York City apartment isn't functional yet, but I'm gonna get on Bob and we're gonna get that one going someday. But a lot of the machines are functional, which is exactly why this Bendix G15 is here in Texas. Our goal is to get this functional and get it back up to the museum in Maryland, so that way people can actually experience a Bendix G15 in person. So Bob, thank you so much, and if you're watching and haven't heard of System Source, go check them out immediately. But since we are trying to get this thing functional, it's been a bit of a journey. So far, we've managed to bring the AC up, but the power on this thing comes up in stages. We can bring the AC up by flipping the big switch right here on the front, but all that does is kick off all 5 of the cooling fans, spin the rotating drum memory up, and warm up all of the vacuum tube filaments. The DC is still completely locked out, so none of the capacitors see any power, none of the diodes see any juice, so it's pretty much just kind of sitting inert at that stage. But because the rotating drum memory is spinning and there is magnetic flux on that drum that is inducing a current into the read heads, we were able to check that the clock track and timing track on our rotating drum are good. So we have a very good foundation to go forwards from here. Now, to bring the DC up, all we really have to do is push this green button right here. That kicks off the sequencers and starts bringing the DC up, and then you can adjust it and make sure that everything is working well. But we don't want to push that button just yet, because when you do push that button, something pretty important happens. The paper tape reader up here kicks off, reads in a number track, and writes it to the rotating drum. This number track is kind of like laying down the encoding on the drum so that the computer knows where to put data. It's really fascinating that it does that from the paper tape reader, but what that means is that the paper tape reader has to be working correctly. Now, there's something really interesting about this paper tape reader. This is 1956 that we're talking about here. So I was expecting this to be a mechanical paper tape reader, but it's not. And that leads me into an interesting paper that I found here. This is money. This is the price list for the Bendix G15 from 1958. Now, this machine has a lot of vacuum tubes in it. It has 460, I counted. Has a lot of diodes in it. But other than that, there's not really too much going on in the way of exotic materials. So when I looked at the price, that seemed a little weird to me, because the G15 general purpose computer here is listed with a purchase price of $49,500 in 1958. In today's money, that's $500,000. So where is all that money going? Well, there's 2 things in here that I find absolutely fascinating. The drum, I am like 95% certain, is actually made of titanium. Yes, titanium was very hard to get your hands on in the 1950s, but Bendix had a strong link with the government and with defense and with aviation, so they would have been able to do it, and US production of titanium was ramping up pretty dramatically in the late 50s. But also, on the paper tape reader up here, it's optical, which means they have photodiodes. I think this might very well be the earliest use of an optical paper tape reader in history, Maybe if you know of something earlier than 1956 that used photodiodes for an optical paper tape reader, leave a comment below because I haven't found anything. And I think that's absolutely fascinating. That's really exotic materials. So if we're talking about throwing those into the price tag, that $49,000 starts to make a little more sense. So what I want to do today is get this paper tape reader out of the machine and onto the bench. There's a couple of things that need work on it, but mostly I want to get my greasy paws into it and make sure that all the movie bits are properly lubed up and everything is cinched down and ready for power to go into it. So we got some work to do. Let's just hop to it. The reader and punch are on this cool little sled that slides forward. However, the rails aren't set up in a way that lets it slide all the way out. There's no latch or clasp or anything. And to make matters worse, the main loom from the machine bolts into the sled. So this thing is going to have to come out the hard way. But it also looks like I'm not the first one to take a swing at this. Most of the bolts are already loose or missing, and this thing is only barely being held in place. You can see this bolt is missing its nut completely, and this one was only finger tight. I didn't even need any tools to get this loose. The main harness bolts, though, were still properly tight, so out came the screwdriver and I methodically went through and removed the 8 bolts. And with all of those out of the way, I can finally swing the loom free. There were 2 more bolts in the back on the rails, and with those loose, the entire sled, with rails still attached, was ready to remove. It's a tight fit and it's not exactly lightweight, so it took some careful finagling, but eventually I got it free and over onto the bench. Now we can get a better look at just how loose one of the drive motors is. Let's start taking this reader portion apart a bit to see if we can get better access to some of the components. And we'll start with the top cover. After removing the 4 screws, it lifts right off, and we can get a good look at some of the interesting design going on underneath. Next, let's shift over to the punch mechanism and remove the side plate from it. This gives a great view of the insanity hiding out underneath here too. Finally, let's see if we can separate the 2 components from each other. The reader is held onto the rails with 4 bolts coming up from the bottom. With those 4 removed, I just have to undo the 2 bolts holding the loom in place, and then it all slides free. Let's get everything back upright to make it easier to work on. And finally, let's pull off the cover of the punch mechanism so we can get to the inside of it. That all came apart relatively easily, and I was actually able to get the 2 halves separated. So this is purely punch related, and this is purely reader related. And with these 2 completely separated, it turns out they're just like completely isolated systems, totally unrelated to each other. They just happen to share the same sled. But with these completely separated like this, I have really good access to everything, so I can go through and make sure that everything gets nice and clean, and it desperately needs it. There's Chad and all sorts of gross stuff everywhere on this. But it also means that we can do any preventative maintenance that we might need to do while it's all apart here. However, how do we know what needs to be preventatively maintained? Well, looking at the reader over here initially, you look at it on the top here with the cover off and you go, yeah, there's some parts in there that look really gross. I'm gonna need to replace those. Most notably these 6 components here, these 4 kind of round cylindrical things on the bottom, and then these 2 here. And boy, these sure do look a lot like capacitors. But you know what? I'm not going to replace those, and I'm going to burn a little bit of time here so that everybody who disagrees with me can pause the video and get into the comments and leave scathing comments about how I should absolutely replace those capacitors. But for everybody else that's still watching, the reason I'm not going to replace those capacitors is because they aren't capacitors. They don't need to be replaced. The 4 cylindrical components here on the bottom are actually diodes, and they just have a rubber vinyl sheathing over top of them that has gone bad. And then the 2 skunky looking components up here are actually iron core RF chokes. They're coils of wire. They should also be totally fine. So I am not going to replace any of the components here on the top that we can see. There are some electrolytic capacitors up here. There's 6 of them. These are the Gudman 0.1 microfarad capacitors that we see lining here. They don't look like they're leaking. They don't look bad. So I'm going to leave them in place, assume that they're working, and if something doesn't function correctly, then we're going to dive into it and see why it's not functioning correctly. But what do these components do? What do these diodes and the iron core do? Well, we also happen to have the schematic for the full reader right here in the manual. We have 115 volts AC coming into this RF decoupling filter that is a combination of 0.1 microfarad capacitors and those 50 microhenry inductors. This eliminates any kind of radio frequency interference that's going to be showing up on those lines, and it turns out that that's quite important, not only for the motors, but for the light that's going to be shining through the holes of the paper tape into the photodiodes. Because we can see that coming out of this, we hit a relay pretty much right off the bat. Says F and R. This is the forward relay and the reverse relay, and those are normally open contacts. But if it is moving forward or backwards, the AC power passes through, comes over to this transformer on the far right that drops it down to 28 volts AC, and then goes to the light. And this is the light that shines on this little steel reflector right up on the front here, and then flashes into the photodiodes so that we can read the data that's coming across. Now that is also additionally controlled by 2 normally closed contacts on the wind and the rewind relays. So we have a pretty finite area where the light is turning on, and well, that makes sense. Now using relay logic like this happens throughout the rest of the control here. These are massive relays that are right up here on the top with multiple poles on them. So it's actually only 2 relays in total, but there's a ton of connections on them. And depending on which connections are on or off, the motors are spinning in one direction or the other. So the actual motor control on this is almost entirely relay based. Now the photodiodes are a little different. That's on this section down here. We can see here that it's showing level 1, but level 2, 3, 4, and 5 are all the same. And energy is not supplied to the photodiode unless there is a sprocket gate being set. So what's happening here is that as that sprocket hole in the very center of the tape comes across the opening, the photodiode will receive light through that hole. And when that happens, that pulls the grid in a different direction, allowing it to conduct, which then sends energy down around through the sprocket gate to the individual photodiodes that are then reading the data. So those photodiodes aren't actually doing anything until that sprocket gate hole is red. The photodiode is going to conduct or not conduct depending on whether light is hitting it or not, and that is going to change what the value of the grid is. There is an 18K plate resistor, it looks like, and then it goes through a 51K resistor and then on out to level 1 logic circuits. So interestingly, motor control and photo read are again completely separated systems all within this same box here. So thankfully, by having this schematic, we can kind of figure out what needs to be replaced. And honestly, I don't think anything needs to be replaced. I am going to leave it just like it is and clean it up only. I am also going to properly mount the motor that's loose in here. I don't know how that got loose, but that's something that we need to work on. Now, let's get to the elephant in the room. It's been sitting right in front of me, this big row of red selenium rectifiers here. And yes, those are indeed selenium rectifiers. Now, there is a bunch of skunky looking cylindrical components over here. And again, those look like capacitors that might need to be replaced, but just like the reader over here, those are actually silicon diodes with a little piece of vinyl tubing over them that's gone off. The silicon diode is probably totally fine. So we are not going to replace those, but yeah, we might need to do something about those selenium rectifiers. Before we do anything with that, let's try to understand what those selenium rectifiers are doing. And this is the schematic for essentially what you're looking at right here. So we can see that right off the bat, right in the middle, we have 6 gas-filled tubes. So that's what this little black dot in the bottom corner of the tube means. And these are actually 2D21 Thyratrons. That's these 6 tubes that are in a line right here on the end. These are very interesting tubes. They're not like regular vacuum tubes, they have, I believe, xenon gas in them. And so when enough current flows through them, something called Townsend discharge happens that creates a sort of cone of plasma that connects the anode to the cathode and allows a phenomenally large amount of current to pass. That makes these wonderful for driving relays because relays require a lot of current. The only issue though is that once they're conducting, they continue to conduct until you interrupt the flow of current someplace else. And I'm not entirely sure how they're interrupting that current. It might have something to do with this punch cycle center thing that's going on up here. But that has nothing to do with our little rectifiers here. We have plus 160 volts coming in and going through the coil of the relay, then through a resistor that is a 700 ohm 5 watt resistor. And then it goes and splits and goes in two directions. It goes to either CR7 or CR1. CR1 is just a freewheeling diode. So whenever we cut off current, the coil in the relay is going to store a bit of energy and it's going to try and dump that energy somewhere. So CR1 gives that energy a place to go. And CR1, if we look at our little list over here, is one of the silicon diodes that is right here on the end. Now these shouldn't see a whole lot of current. It's just kind of giving a place for stuff to go in a circle. But the other diode, CR7, does see some stress. So it goes into the anode of the 2D21, and if the 2D21 is conducting, pin 2, the cathode, connects up to, I believe that is saying 0 volts. So we'll have 160 volts being dropped across the relay coil, the selenium rectifier, and the thyratron. So CR7, the resistor, and the relay are going to see a lot of power. So these are definitely heavily stressed selenium diodes. And well, I don't know, man. I waffled a lot about whether to replace these. They're probably fine, but if they do go up, it's going to release an incredibly terrible smell, I've been told. Thankfully, I've never had to smell a burned up selenium rectifier. But I think we can replace these relatively easily and leave them in situ. Now, whenever you replace a selenium diode with a modern silicon diode, the modern diode has a lot less voltage drop across it, and I think the difference is not going to make any impact whatsoever. So I think what we'll do is we'll just snake some very small silicon diodes in there on the side, break one of the connections there, and just leave everything looking like it's totally factory, and then just have a little modern diode hiding out in there. And I think that covers the electrical side of everything, but all that's left is the mechanical side. And you can actually see a bit of the mechanical side here, but the actual mechanical punch mechanism is on this side over here. And I have been told by some people that I trust very much that this is 100% identical to the punch mechanism that came out of a Frieden Flexowriter, which is a pretty fancy teletypewriter. So that is a Frieden Flexowriter punch. I know absolutely nothing about it other than the fact that it's just a piece of mechanical stuff. So it needs to be cleaned and the spinny bits need to be oiled. So I can actually see some of the bearings here, which means I have pretty good access to everything. It should clean up and start working nicely. Now, of course, we won't be able to test any of this until we actually flip DC on. And we're obviously not going to do that today because we still have a few more things to tackle. But what we can do today is get all of this cleaned up, maybe do some work on these selenium rectifiers, and then get it all back into the machine. So, well, I got more work to do, so I'm just going to get to it. To clean this thing up, I'm going to lean on my favorite cleaner, Simple Green. It is, however, a bit of a tight squeeze everywhere, so I'm going to use a toothbrush to work the cleaner into all the nooks and crannies. When cleaning up mechanical bits that need to rotate or slide, I switched over to a toothbrush soaked in 91% isopropyl alcohol. This worked really well at freeing up all the nasty gunk that was keeping everything seized in place. On the backside here, I continued my cleaning escapades. The goal was to get everything free enough to turn the mechanism by hand. Ultimately, the motor will drive it via the V-belt, but that belt is not long for this world, unfortunately. I'll have to get a good measurement of it and see if I can find a solid replacement for it.
Eventually though, everything starts to free up really well. Once clean and moving, I soak all the bearings and slidey bits in oil to really free them up and get them moving smoothly. Eventually that oil will probably have to be replaced with some kind of sticky grease, but until I can power it up and let the motor really work the oil in and out, this will work for now. Over on the reader, it's more of the same, just scrubbing away, trying to get everything as clean as possible without having to massively dismantle it. There were 4 vacuum tubes hiding out in the reader that got pulled and cleaned up, and then of course there are 6 thyrotrons hanging off the edge of the punch. These also all got pulled out and properly wiped down.
The final step is to do something about these selenium rectifiers here. There's 6 of them here, so we got to do whatever we do 6 times, and I've actually already done the top one here. You can see there's a new diode just sitting right along the top here. All I did was I took the wire that comes off of the bottom side of the diode and goes into the PCB below it and desoldered it. I'm grabbing it with the hemostats right now. It's just pushed out of the way. This effectively pulls the selenium diode completely out of circuit. Then I put a 1N4007 in place of it. I soldered it directly into the PCB where that wire went to, and then soldered the top half of it to the selenium diode up here. This allows the selenium diode to completely stay in place, and the new diode is almost invisible. As a matter of fact, I think anybody who's looking at this that doesn't know immediately what they're looking at probably wouldn't even notice it. So it's very easily and quickly reversible if we want to go back to running the original selenium diodes in it, but I think that's going to work out really well. Now I just have to do 5 more of these.
I'll go ahead and knock out the next one for y'all just to show you how easy it was to do this. I just used the hemostats to grab the lower wire and then heated up the solder on the PCB with the soldering iron, letting me pull that wire free. With the wire twisted safely out of the way, I then snake the new diode down the side and rest it on the pad. Then I just heat the pad up with the soldering iron until the diode pushes through the through hole. I follow that up with a strategic bend of the upper lead, then solder it to the top part of the selenium diode where the second wire solders to. Nice and stealthy and surprisingly easy.
There we go, we got the paper tape punch and reader back on the sled and slid back into the machine. Everything is plugged in and ready to go. I did leave all of the covers off of it, like pretty much everything else on this machine, because I'm fully expecting that when we bring the DC up, very little is going to work like it's supposed to, and we're going to have to do some troubleshooting, and I'm fully expecting there to be some troubleshooting done on this. We didn't do that troubleshooting today because this thing needs a lot of voltage rails coming into it. I think it needs like plus 160 volts, plus 100 volts, 120 AC, and some negative voltage rail. So it needs a lot of different rails coming into it, and the best way to get those rails to it is to just push the green button and let the machine generate those voltages for us. Now we're not quite ready to push that green button yet. We are getting very, very close though. There is a few more things that I want to tidy up on this machine. The big capacitor bank here on the bottom, I want to pull that out, make sure that none of those are shorted, put some electrons in them and try to reform them if they even need it, see if they hold a charge, and then get it back in there ready to go. There is also, the last time that I had it spun up, I noticed that there's a few tubes that the filaments didn't come on, so I want to go through, look at every single tube while the AC is on, and replace any that look like they have burned out filaments. Now, I didn't go through and test every single tube. Like I said, there's about 460 vacuum tubes on here, so I'm just gonna assume that most of them work and only really start troubleshooting and testing tubes when we get to a part of the machine that isn't functioning like it's supposed to. Finally, the last thing that I want to do on this is there's still those kind of modification wires that are kind of haphazardly strewn about, and I want to tidy those up at the very least, and one of them on this door is broken. So presumably those modification wires were there for a very specific reason, so I want to replace the broken wire and refix that modification connection, and then this chassis will be completely ready to bring DC up. However, we can't do that until we plug the typewriter into it, and the typewriter's looking a little worse for wear. So we need to dive into that as well. So we still have a little more to tackle before we get to the point of bringing DC up, but I genuinely think We're going to be bringing DC up on this thing sometime in the middle of summer, and I'm fully expecting to be executing code by the end of the year. This project is shaping up absolutely amazingly. I am super excited about it. So I want to thank you guys so much for tagging along with me on this journey, and I want to thank you so much for watching the videos, and I hope to see you next time.